In the early 1890s, Westinghouse had stopped work on the Tesla motor. This was largely due to the fact that their early alternators were 133 and 125 Hz and single phase. Because of this high frequency, they proved to be unsuitable for the operation of the induction motor. These early alternators bore little resemblance to today's machines. They had rotating armatures and stationary fields. As such, they bore a striking resemblance to DC generators of that era. The alternator shown here, in which Tesla played no role, was installed in the Gold King mine at Telluride, Colorado around 1892. The motor used at Telluride to provide power to the mine's operation was a single-phase motor that was almost identical to the standard Westinghouse alternator just mentioned. As such, it was not self-starting. Tesla's part in the Telluride project was the use of one of his induction motors to start the single-phase synchronous motor. Conventional wisdom, both then and now, has it that this was the proving ground for Tesla's motors. This first application of his motor at Telluride was, well, less than successful. This is discussed in some detail in the historical technologist video, Industrial Motors, the Early Years. In the 1914 edition of the Electric Journal, the manager of engineering at Westinghouse, R.S. Veach, wrote that the partial failures of the early Tesla motors were almost entirely due to the lack of understanding at that time of the fundamental principles of electric and magnetic circuits pertaining to alternating currents. In those early years, Westinghouse employed several engineers who would go on to have a great influence in the electrical field. Two of these, Charles Scott and Benjamin Lamy, would make major contributions to the development of power transmission and motors. Initially, Scott worked with Tesla to get his motor ready for manufacturing. Scott, a graduate of Johns Hopkins University, was to become a major player in the field of electrical power transmission. He developed a Scott connection used to connect two-phase to three-phase systems. In 1902, he was elected president of the American Institute of Electrical Engineers. Benjamin Lamy, a graduate of Ohio State University, was to become the driving force behind the use of the cage winding now used in all squirrel cage induction motors. The generators at the first Adams plants in Niagara Falls, New York, were his design. Lamy soon realized that part of the Tesla motor's inherent weakness was related to the polar field construction shown here in Tesla's patent 381968. Although the polar field was the norm at that time, it was both economically and technically unsatisfactory in an AC system. The basic problem was that the flux at the adjacent poles did not overlap each other. This was soon changed. The conductors were installed around the periphery of the stator in such a way that a uniform progression of the rotating magnetic fields from two- or three-phase AC circuits was possible. With the same expenditure in magnetizing current, an increase to 2 or 3 times the total flux meant a revolutionary improvement in the characteristics of the machine in general. Benjamin Lamy's patent, US 633856 of 1899, shows such a distributed winding. The change to distributed windings was likely the most important contribution to induction motor technology made before the end of the 19th century. This is the stator of an induction motor of the early 20th century. The conductors are placed in the stator slots. All phases are arranged in a manner that will produce a rotating magnetic field. This diagram shows a typical arrangement of conductors in the stator slots. From the time of the acquisition of Tesla's patents to the Westinghouse's display of a 300 horsepower induction motor at the 1893 World's Columbian Exposition in Chicago, work on the induction motor was sporadic. The following information is taken from Benjamin Lammy's 1921 AIEE article, The Story of the Induction Motor, on page 203. The original double column is difficult to read, so I've enlarged the parts we'll deal with. We'll only touch on a few aspects of induction motor development in Westinghouse. I recommend that you read the entire 21-page article. On page 204 we read, "Considering the lack of knowledge of magnetic problems and conditions of those days, it is really a source of surprise that Mr. Scott developed the motor as far as he did. He developed a slotted secondary with overlapping distributed windings up to a quite effective point." These early Tesla motors, as developed by Mr. Scott, showed quite good operating characteristics that might have proved commercial with suitable supply circuits. Yet the motors were fundamentally handicapped in one feature, the primary flux distribution. In those days, distributed field or primary windings were unknown, and only the simple polar types of magnetic construction were recognized. In consequence, these early induction motors were made with distinct polar projections, each projection carrying a primary or field winding with alternate coils belonging to one phase of a two-phase circuit. The flux, therefore, of the adjacent poles or phases did not overlap each other as in a modern induction motor, and uniform progression of the magnetic field as we now understand it was not possible. When it became apparent at Westinghouse that the lower frequency polyphase circuits required would not be available in the short term, Scott realized that he was fighting a losing battle for the motor. Development work on the induction motor was stopped in 1890 and did not take up again for approximately 2 years. The first Westinghouse motors with distributed windings, both primary and secondary, were tested in 1892. They were designed for operation at 60 Hz, then referred to as 60 cycles, and were ready for market in 1894. At Westinghouse, the primary was the rotor. The secondary was the stator. At GE, the secondary of the motor was the rotor, and the primary was the stator. By the early years of the 20th century, all induction motor manufacturers had adopted GE's arrangement. Shown here is a typical three-phase slip ring assembly, with 3 collector rings and 3 sets of brushes. These early motors were generally connected to the power system through power resistors. These power resistors, highlighted here, were inserted into the supply circuit to reduce the voltage applied to the motor and thus limit the current while the motor was coming up to speed. Power is applied and current flows through the resistors to the motor. As the motor speed increases, the S1 contactors are closed, shorting out a section of the resistor bank. This in turn increases the voltage supplied and allows for more current to flow through the motor, further increasing its speed. After the motor is accelerated further, S2 is closed, shorting out all the starting resistance, applying full voltage and allowing the motor to reach full speed. The problem with this method of starting was that the resistors wasted energy, often getting too hot to touch. Around the turn of the 20th century, a more modern version of the control system had come into use. The starter shown in the diagram used an autotransformer to reduce starting current. This special transformer doesn't have 2 independent windings as a regular transformer does. As such, it is cheaper to manufacture. When the S contactors are closed, a voltage is applied to the motor that is less than the line voltage. This reduces the starting current. Closing the R contactors and opening the S contactors connect the motor to full voltage, allowing the motor to reach full speed. Unlike the rheostatic control just mentioned, the voltage is reduced without the wasted power incurred in a resistor. Shown here is an autotransformer starter with a cover in place. Here the cover is removed to show the starter's components. 1, 2, and 3 are the incoming power conductors. A, B, and C are the autotransformers. 3 power fuses are shown in the diagram. S is the lever used to switch from start to run. This starter was a complex device that added to the cost of an induction motor. However, only the smallest motors could be used without it. By the end of the 1930s, full voltage across-the-line starters for motors up to 200 horsepower were coming on the market. The days of autotransformer starting were coming to an end. But much more work was required to bring the induction motor to the point where, today, it is the go-to motor for 90% of the world's motor applications. Solving the harmonics problem was the next major step. This diagram shows the first 4 harmonics of an approximation to a square wave. The steeper the step, the greater the number of harmonics, each with a higher frequency and its attendant losses. Although doing away with Tesla's salient poles helped reduce harmonics significantly, there was much left to do. It was soon realized that this complex phenomenon required a person trained in mathematical analysis. One of the first math specialists hired at Westinghouse was Bertha Lamy, Benjamin Lamy's sister. Her mathematical skills greatly assisted in the understanding of the motor's harmonic problems.